Hello everyone, and very warm welcome to this doubt clarification session for this course on mathematical foundations for machine learning. I've been going through the forum questions and have been answering all these questions, and we thought we would do this module by module doubt clarification or interpretations, whatever we could not cover in the regular weekly classes. We thought we would take it up now. So this whatever session that I'm going to do right now is going to be on exclusively on linear algebra. What is its relevance in machine learning and all. So we have studied a lot of things in linear algebra, which we started with the idea of fields, and many of you even had questions about what is the necessity for a field. And I told even in all the forum answers we have said that the field is an essential mathematical structure for you to create a vector space, and then the operations on the vectors are basically element wise operations on the field elements. That is why the field is important. So in fact there were a couple of questions there which people asked about why did you choose R6 and then say that it is not a field, what is so special about it. Now we should not get misguided saying like the set of integers modulo any integer, positive integer is going to be a field. So that should not happen, and that is precisely why that example was given. And going further, we had a lot of other questions too which we answered. We have in fact we have got a couple of questions from some of the registrants for this course. I am sure we will try to answer most of the questions, and if not we will move it to the subsequent weeks.
Hello sir, this is Niranjan, and I had a few questions to be asked. First one is, why is the concept of vector space central to many machine learning algorithms?
I hope you heard what Niranjan asked. He was asking like why is the concept of vector space central to the idea of machine learning algorithms. Of course, see, the most important stuff that we must understand is when we collect data, when we collect different parameters from samples, by sample I mean okay it would be a person with individual medical parameters or individual course marks or whatever that is, we collect it. The first thing that we do is we tabulate them. The moment you tabulate them, you are going to get rows and columns. The moment you are into rows and columns, you get into the idea of vectors. The moment you are into the idea of vectors, it becomes easy to do everything with geometry, everything that we have done with linear algebra, all the ideas and all the concepts that you have studied will become applicable on those data that you have collected. It helps you understand the data much better than the table that you have just collected and kept. Therefore, the idea of vector space is extremely essential because you can transform the vectors. That means the data that I have collected, it may not make sense to me directly. So what I can do is I can transform these, and then to get a meaning out of these data you can do you can apply all kind of linear transformations that you want without altering the information conveyed by the data. That is very essential. When you do these transformations, typically what happens is, I mean when you try to manipulate with the data, you tend to lose sight of the information that the data gives. But with the idea of vector spaces and linear transformations and other things, the original information that the data is going to give you is preserved. There is no what would you say, there is, I mean there is of course when we look at SVD and things, you will see that there is a loss, but that is not going to be great. So the information is basically preserved as far as application of linear transformations and things are concerned.
Okay, the next question is, in what ways do linear independence, basis and dimensionality impact the performance of machine learning models?
So the first of all we must understand this linear independence is a very interesting and important concept, because we saw in the case of vector space, linearly independent set of vectors was named as the basis for the vector space. That means it is used to generate the entire vector space. So we had basis which is basically the set of linearly independent vectors, right, set of linearly independent vectors. Now what is interesting is, in the geometric sense we saw that the basis is going to be the generating set for the vector space. So this is a generating set for the vector space. And how does it find itself applicable, these ideas applicable in the domain of machine learning? Whenever we talk about machine learning, we look for features, and there could be features which are redundant and there could be features which are independent. Now the moment we talk about linearly independent vectors and so on, we are talking about linearly independent set and of features. Basically we are looking at independent features. So the idea of independent features is very essential, because when you have redundancy you have huge volume of data, and redundancy is going to cost a lot in terms of computation. So what we do is we try to eliminate this redundancy, and when you try to eliminate, or when you eliminate this redundancy or redundant features, we end up getting independent features, which actually helps you understand the data much better. See, it is like saying I am going to look at the set of students, let us say in an engineering college. Now if I were to say this, and then if I add one more feature, what is the age of students in this engineering college, I mean it typically does not make any it does not give much more information except if there are some outliers, because you know that in an engineering college where the undergraduate population is more, the age of the students is going to be between 18 and 22. Therefore asking separately for this age might not be a good idea. Maybe the other example that we can look at is, suppose I say that okay, there is an exam in which the exam was for 100 marks, and then some 100 students have scored 100 on 100. Now does it make sense to ask how much mark the student has scored in question number 9 or question number 10? It does not really make sense, because that information is already conveyed by the fact that the students have scored out and out in the exam. So asking for question number 9, the mark scored in question number 9, is basically a redundant question that you ask. So we need to eliminate those dependent features, features where there is going to be correlated features. That is what we call. We will do it when we do probability and statistics, you will understand this better, right. So you will know that better. So what we say is, like, the idea of independence, basis, dimension is extremely, these are all extremely important as far as machine learning is concerned, because you talk about features, independent features and so on. I hope that clarified the point.
Hello sir, this is Amudan and I have a few questions. The first one is, what does the rank nullity theorem reveal about the structure of linear transformations?
So hello Amudan, I guess you asked this question, what do you mean by rank nullity theorem? What does rank nullity theorem reveal about the structure of transformations? So very interesting question indeed. Rank nullity theorem, I think I made a passing remark as far as the lecture is concerned in the second week when we did linear transformations, but we did not really look at it in deep. We will just get a grip over what rank nullity theorem is and why is it very important, right. So let us look at the idea of a rank nullity theorem. Right. The first thing that we must understand is, like, we see what is the rank and what is nullity in the first place, and then see what it actually means to say a rank nullity theorem. That makes it better, right. So let us look at this. So what is this rank? Remember, when we looked at the linear transformations, we said that, look, there are subspaces associated with any linear transformation, and two of those subspaces are the fundamental subspaces that we have seen are basically the null space of the transformation linear transformation T, null space of linear transformation T, and the which we also called as the kernel of T, and we also had the range of the linear transformation, which we also called as the image of the transformation T, which in terms of the matrix we called it as the range space of the matrix A, range space of the matrix A, and null space of linear transformation T was basically called the null space of the matrix A. And the moment you say these two are subspaces, each subspace is basically associated with a dimension, and null space has a dimension which is called the nullity. The dimension of the null space is basically called the nullity, which I will use this notation nu A. Okay. So, the null space dimension is nu A, and what does that actually mean? This means nu A number of vectors are there in every basis of the null space. Null space is a vector subspace. The vector subspace therefore has a basis, and the basis consists of a set of vectors, and the set of the number of the cardinality of this basis of any given basis for a vector space or a subspace, you call it as the dimension. In specific, the dimension of the null space of the linear transformation T is called as the nullity of transformation T, or nullity of the matrix associated with it, which we call it as nullity of A, where A is the matrix associated with T, the matrix which represents or associates the linear transformation T, matrix representation of T, right, that is what it is. Now, we said that range is also a subspace of the linear transformation. What was the range basically saying? While the null space said the set of all vectors which get transformed to the 0 vector, null space was basically the set of all vectors, let us say x in let us say Rn, such that the transformation of this x vector in Rn is basically, it results in the 0 vector, right. This is the 0 vector. I mean, it could be back into Rn or it could be into this space Rm, whatever that is. Okay, we'll just say that the null space is nothing but the set of vectors which gets transformed to the 0 vector by the transformation or by the linear transformation T. Now, what is the range of the linear transformation? Range of the linear transformation is basically the set of all those B vectors which can be expressed as the transformation of x. So, what do we mean by this? Suppose if I represent this transformation T by a matrix A, then I am going to look at the set of all those B vectors which can be written as X. So, you keep changing x, you will get different b's, and then you collect all that and then put it, and that is what is going to call, we are going to call as the range of the linear transformation. So, this range of linear transformation or the image of the transformation basically is a subspace, and this subspace has a dimension, and that dimension is what we called as the rank of the linear transformation or rank of the matrix A, where A is the matrix representation of this linear transformation T. So, now the question is, how do we put these two together? Can we make some sense out of these two together and then say, okay, get some interesting fact out of this. So, what did we say? We have two subspaces, one the set of vectors which get transformed to 0 vector, we call it as null space, and the dimension of that is what is called as the nullity, which is called the nu, which is represented by nu A, and the other one is the range of the linear transformation, which is the image or the set of vectors of what we call the set of vectors which get transformed to this vector B. So that is what we called as the range of the vector space, and the range is a subspace. I mean the range of the transformation, sorry I said vector space, range of the subspace, sorry, range of the linear transformation, and the dimension of the range is called the rank of A. Now the question is, how do we put these two together? And that is exactly where our rank nullity theorem comes into picture. So what does it say? Rank plus nullity is equal to dimension of the vector space. Right, it is basically the dimension of the vector space. Okay, so what is rank and what is nullity and what is the dimension of vector space? Let us put all of these together properly. So we say that, look, let V be a vector space, let, okay, we will say of dimension let us call this as dimension of V. We do not even know what that number is, let us call that as dimension of V, right, associated with the linear transformation T. Linear transformation T, right, and let NA be the null space of T, of dimension nullity of A, and let R A be the range of T. We already defined what these are in our regular lecture, range of T, dimension, let us say let me call that as rho A. Now what it says is rho A plus nu A is equal to the dimension of the vector space V. So what does it say? It basically says the rank plus nullity is equal to the dimension of V. Now how do we interpret this further? Let us look at this. I have a matrix associated with a linear transformation T. Let me call this as, let us say, A m by n. Basically the transformation T is going to map Rn to Rm. This is a linear transformation, associated matrix is A, associated matrix is A, right. Now what is happening here? I am going to look at this rank plus nullity and things, and then we want to put that in a proper understandable way. So I am going to look at Ax is equal to B. So A will be an m by n matrix, X will be an n by 1 matrix, which is going to give me B, a column vector of dimension m by 1. Basically it is an m component vector. Now let us look at something interesting here. What is that? We are going to say that, look, if I try to solve this, solving Ax equal to B, I am quite sure most of you would have done this row reduced echelon form and Gaussian elimination method, Gauss elimination technique for finding solution to system of equations, and when you tried doing this you would have ended up getting a row reduced echelon form or a reduced row echelon form. Let me put this as row reduced echelon form. These are things which you would have definitely done, like when you try to solve the first 101 level course of matrix theory. in your undergrad would be this row reduced echelon form, solving system of equations and Gauss elimination and stuff, right? Gauss elimination and things. When you do this, you would have been taught the idea of pivot variables and free variables. Pivot variables and free variables, right? You would have been taught this idea of pivot variables and free variables. That means suppose I have x n by 1, I mean x n component vector, x n by 1 means I am going to have x1, x2, etc., xn. Now we know that if I write this as a11 x1 plus a12 x2 plus etc. a1n xn is equal to b1, a21 x1 plus a22 x2 plus etc. plus a2n xn is equal to b2, etc. am1 x1 plus am2 x2 plus etc. plus amn xn is equal to bm. I will rewrite this in a different way, where I am going to write this as linear combinations of the column vector. So what I will do is, if you look at the previous set of equations, the entire first column seems to be multiplied by x1, the second column always gets multiplied by x2, and the nth column is always getting multiplied by xn. So what I will do is I will write this as x1 into a11, a21, etc. am1 plus x2 into a12, a22, etc. am2 plus etc. plus xn into a1n, a2n, etc. amn is equal to, I have b1, b2, etc. bm. So what do I see? I see that the vector b is written as a linear combination of the vectors which are constituting the columns of the matrix A. This is what we have. Now when you did your row reduced echelon form using Gauss elimination, you would have seen that there are some variables which become pivot. Like when you do do elementary row transformation, you would have first removed the first variable from the second row, then the first and second variable from the third row, first, second, third variable from the fourth row, and so on. That means it starts diagonally, it goes diagonally as you go down. This is what it happens. Otherwise you will have your pivot variable to be on the right hand side in every subsequent row. So you would see that, and the rows of all 0 elements would be appearing at the bottom of the matrix, and that is what we call as row reduced echelon form. Now in that you would have seen you will have some pivot variables and you will have some free variables. The most interesting thing is the number of pivot variables in the row reduced echelon form is what you would have called as rank. When people taught you first year mathematics in matrix theory, they would say, look, row reduced echelon form, count the number of non-zero rows, that corresponds to the rank. Non-zero rows in the row reduced echelon form will correspond to the number of pivot variables, and that is your rank. If that is the rank, then what can you say about the free variables? The number of free variables is what you call as your nullity. So let us write this. So the rank is basically the number of pivot variables in the row reduced echelon form in the RREF of A nullity corresponds to the number of free variables in the row reduced echelon form of A. Now it is easy to understand what is that. Suppose if I have, let us say let us say 5 by 7 matrix. Now 5 by 7 matrix means you will have 5 rows and 7 columns. This is the first column, second column, third, fourth, fifth, sixth and seventh column. Now what happens, I will say that look in the first row, let us say first row, second row, third row, fourth row and fifth row. In the first row, let us say this is the pivot variable, the 1 comma 1 is pivot variable, second pivot variable and third pivot variable. Now what happens is, let us say all the other fellows are all 0, this is 0, this is all completely zeros, this row is completely 0. Now what did we say, that look, there are 3 pivot variables, and if you look at this, you will have 4 columns with no pivots. These 4 columns has no pivots, right. So now what we say, the rank here in this case is 3, rank is equal to 3. There are 4 more variables which are free variables, therefore nullity is 4. Now what does rank plus nullity give me? Rank plus nullity gives me number of columns, and number of columns correspond to the number of variables that you have used, and number of variables correspond to the number of components in a vector, and if there are n components in a vector, you basically refer it to an n dimensional space. So what we are going to say is rank plus nullity is equal to the number of columns of the matrix that represents a linear transformation. Rank plus nullity is equal to number of columns of A, and this is basically number of pivot variables plus number of free variables is equal to number of unknowns, which is equal to the number of columns of A, and rank is nothing but dimension of my image or the range space of A plus dimension of null space is equal to dimension of the vector space, right. So we have rank plus nullity is equal to dimension of the vector space, which is n. Now even more interesting, one more interpretation we will see, this is basically rank of A. Suppose you say a matrix A, I also have the other matrix which is A transpose, which can be obtained from this. Now we know that rank of A plus nullity of A, rank of A plus nullity of A is equal to the number of columns. You would have also seen in week 3's lecture where we talked about orthogonality and then orthogonal complement subspaces, where we spoke about the okay, let us talk about orthogonal complement subspaces of a matrix A. We said that null space of A is the orthogonal complement of range space of A transpose or row space of A, and we said null space of A transpose and the range of A are basically the orthogonal complements of each other. Null space of A basically is an element of Rn, this is also Rn. The other two subspaces, null space of A transpose and range of A, are in Rm. Now the dimension of range of A is what we call as rank of A, which is row A, and this was basically the nullity of A. We said that nullity of A plus rank of A is equal to the dimension of this. We also have one more. What is that? The range of A transpose, we will call that as the rank of A transpose, which is row A transpose. By the definition of orthogonal complement, we see that the dimension of the sum of dimensions of the orthogonal complement subspaces must be equal to the dimension of the space to which they belong to or they are subset of. Therefore, we also see the nullity of A plus rank of A transpose is also equal to the number of columns, which is equal to n in both the cases. So, now what do we see? We see that row A plus nullity of A is equal to row A transpose plus nullity of A transpose, nullity of A, row A transpose plus nullity of A. You have to recollect this picture that we had. We had this, we said this is Rn and we said this is Rm. We have the range of A transpose, we had nullity of we have the null space of A, we had range of A, null space of A transpose, this, and these were orthogonal complements of each other. We had this. Now, if you see these two to be, I mean if you look at the equation, nullity of A appears on both sides, you can knock them off. Therefore, what do we see? We see a very important and very interesting fact. What is that? The rank of A is always equal to the rank of A transpose. So, that is why we always say the matrix A and the matrix A transpose have the same rank. So, this means rank of A is equal to rank of A transpose. And what is even more interesting is, to answer the question that Amudan had asked, the idea of rank is extremely important because rank tells you the number of independent features that you have. The rank gives you, when you collect your data, rank tells the number of independent features you have, right. Rank basically tells the number of linearly independent vectors, that is what, because it is the dimension of the vector space, which means it is the cardinality of the basis, and therefore, we say this rank is going to give me the number of independent features in your data that you have collected. Okay. Okay.
The next question is, how are linear transformations helpful in machine learning?
The next question that he has asked is, how do linear transformations help in machine learning? Of course, linear transformations will help you. I mean, you can do a lot of things. When you say linear transformation, you can rotate, you can do sharing, you can do reflection, you can do all sorts of geometric stuff on the vectors to try to get the meaning or to try to get the structure of the data. Therefore, linear transformations are extremely essential as far as machine learning is concerned. The moment you get your data, if you are not able to understand what the data is in the given form is representing, try to do some kind of transformation on it so that you get a better understanding of the data.
Another question is, why is diagonalizability a desired property?
That is very interesting question, because this diagonalizability means I have a matrix which only has diagonal elements. Diagonalizability corresponds to a matrix with only diagonal elements. Off diagonal elements are all 0, which means instead of m, if I have an m by n matrix, or let us say n by n matrix, let us say I have an n by n matrix, I have totally n squared elements. Now, all the elements other than these n diagonal elements have become 0, which means you are now saving on a number of computations. The moment you have a diagonal matrix, number of computations is reduced drastically. And more important stuff, you would study it when you do your I mean, even in PCA, Dr. Ashok Rao had already talked about it, where you look at the covariance matrix, the data's covariance matrix, and the covariance matrix is where on which you apply your PCA and things. So, when you do this covariance matrix, the diagonal elements are all variances and the off diagonal elements are all covariances. Now, if the off diagonal elements are all 0, it means no two variables are correlated, they are decorrelated completely. That means I am talking about linear correlation. We will see all this linear correlation and things when we do random variables and multiple random variables, but the idea is very clear. The off diagonal elements will all be the correlation values or the covariance values between pairs of features or pairs of what would you call random variables or parameters. Now, if they all are 0, then you say that look, there is no linear correlation as such. We will see why we emphasize on this term linear correlation when you do statistics, but that is what it means, right. So, the first thing, diagonalizability, when you diagonalize it, the computations become very less fewer computations. You remember when we did A is equal to PDP inverse, and I wanted to compute A power n is nothing but P d power n P inverse, which is extremely interesting. Why? Because if I have to compute A power n, A would be let us say A itself, or let me not put this, okay, let me take A power k, so that A power k I will take P d power k P inverse, and assume that A matrix is an n by n matrix. Now you want to do A square, you multiply this A n by n with another, with the same A n by n. Now what do we get? You have to do a lot of multiplications and additions and a whole lot of stuff, which is computationally kind of frustrating. You do not want to do that. If you want to avoid, or if you want to reduce the number of computations, the best way to do is diagonalize the matrix A. The moment you diagonalize this matrix A squared becomes very easy. A squared is P d squared P inverse. You just need to compute the matrix P once and P inverse once. D square says, look, I only multiply these n elements, find the square of these n diagonal elements, which means I have already saved on a lot of computation. So orthogonality, or the idea of diagonalizability, is very important as far as the idea of matrix powers computation is concerned. Diagonal matrix implies what would you call reduced computation. In other perspective, you will also see that the diagonal matrix is going to be some kind of what you call diagonal matrix. If I say, look, the first element is non-zero here, rest of it is all 0, then you have this is 0 and the rest of it below the second element are all 0, and it goes like this, right. You would see this somewhere, this kind of is a standard basis where every element, if you take, like it is like that 1 0 0 1 identity matrix, which means you are getting vectors which are along the axis. You do not have a vector which is there hanging there in a plane, but instead all these vectors are oriented along the reference axis. So that is even another interesting decomposition that we have had, right. Okay.
Another question is, how does orthogonality simplify computation?
How does orthogonality simplify computation? That is the most important thing. Orthogonality simplifies computation. Suppose I want to solve Ax equal to b. We will go here everywhere. Finally what we want to do is we are trying to find out the solution to Ax equal to b. I want to look at Ax equal to b, or I want to look at b, which is the vector on the right hand side, is going to be a linear combination of the columns of this matrix I have this linear combinations of the column vectors. Now what I want to do is I want to find out what are the coefficients or what are the scalars that I need to multiply these vectors with, so that I get that vector b. Now if we want to find it out with a normal set of linearly independent vectors, usual set of linearly independent vectors, I require solving the system of equations, right. What does it mean? I have b1 is equal to a11 x1 plus a12 x2 plus a1n xn, and let us say bm, this is equal to am1 x1 plus am2 x2 plus etc plus amn xn. If I want to find out x1, x2, xn, which are basically the scalars that are associated with each of those column vectors, in order to get this specific vector b, I have to solve the system of equations. Solving the system of equations is a painful process. Iteratively you can use Gauss elimination and all those things, but it is a painful process. However, if the column vectors are orthogonal to each other, let us say a1, a2, an are all orthogonal to each other, we have already seen this as when we did the orthonormal basis, and we call that as the Fourier expansion, Fourier basis expansion. When you have orthogonal vectors, orthonormal basis, then it is easy to figure out what is the value of b, what is that linear combination which is going to give this b vector. It is simply b dot the a1 vector in the direction of a1 vector plus b dot a2 vector in the direction of a2 vector plus etc. b dot an vector in the direction of the an vector. That means I just take the dot product of the given vector with each of those elements of the basis. Oh, that gives the coefficient, that gives the scalar, and that is precisely what we are looking for. Obtaining the what would you call, obtaining the coefficients becomes very easy if we have orthonormal basis or orthogonal vectors. Number 2, when you say orthogonality, what do we mean by that? Look, the two vectors are at 90 degrees to each other, that is the meaning of orthogonality. When the two vectors are orthogonal to each other like this, I have this vector and I have this vector, these two are orthogonal to each other. Now what happens is, there is absolutely no shadow of this vector along this direction, which means they are already uncorrelated, they are decorrelated vectors. There is no information of this guy along this direction. That means there is no correlation, there is no similarity, nothing is there. Therefore, orthogonality is extremely important. Is there any other case where orthogonality is essential, where it is sought after? Of course, yes. If the matrix A is an orthogonal matrix. Now, how do we define orthogonal matrix? The columns orthogonal matrix means the columns of A are orthogonal to each other and each column vector is of unit length. If each column vector is of unit length, then what happens? I will say A inverse, if this is the case, then A inverse is equal to A transpose itself. Orthogonal matrix has a very important property that the inverse of the matrix, if the matrix A is square, then the inverse of the matrix is equal to the transpose of the matrix. This is another reason why orthogonality is important. And last, maybe there are many more, but I will stop with this particular thing for orthogonality. The last important thing that comes with orthogonal matrix or orthogonal transformation is the fact that it preserves length, it preserves shape, it preserves everything. There is absolutely no loss of any information as far as the measurements are concerned. Isometry is what we call it as, right? It preserves the scale, it preserves the length, it preserves the shape, it preserves everything. Therefore, orthogonality is extremely important. It is not just about computation, it has got a lot of important features as far as machine learning is concerned, geometry is concerned, a whole lot of things. Okay.
How does SVD help in data compression, and what are the key limitations of SVD, PCA and SVM while applying it to the real world data sets?
Okay, this is going to be the last question that we are taking for this week. I think Niranjan has come up with another question. He is asking like, how does SVD help in data compression in machine learning? What are the limitations of SVD, PCA, SVM when applied to real world data sets? And how do these limitations affect the performance in machine learning tasks? So, this is something which he has asked. How does SVD lead to data compression? Very important thing. As far as the moment you say data compression, I take huge volumes of data is what I have. Let's say I take like 10,000 parameters across, let's say 1 lakh samples. I take 10,000 parameters. It need not necessarily be that all the 10,000 parameters that I take play a significant role. There could be some relation between these 10,000 parameters that I take. Therefore, the rank of the matrix of the data matrix is going to give me the number of important features that I have. The moment I look at that, SVD is going to basically give me a low rank approximation of the entire matrix that I had, which means I have already saved on computation. What we call PCA and SVD and all those things. These are basically compression techniques in the sense it takes only those R significant vectors, the R vectors it takes, and then say, look, I am going to use these R vectors where R correspond to the rank of the matrix. So it already has achieved compression. Suppose I have as I said, like 1 lakh by 10,000 matrix, of which only, let's say, some 1,000 variables are important, then the entire information or the structure of the data lies in a 1,000 dimensional subspace rather than that 10,000 dimensions vector space. So by looking at the 1,000 dimension vector space or the subspace, you already have achieved significant compression, right. So SVD is essentially a compression technique. Of course, you can reconstruct, you can do a whole lot of things. So that's about SVD. Of course, when you talk about limitations of any of these things, first of all these things are like SVD and PCA typically are associated with linear things. Wherever there is linear relation, you do that. If there is a non-linearity, these guys will be a problem, these guys will not work. And second thing is computation wise, they are going to be quite expensive. And as far as SVM is concerned, of course, the choice of the kernel is very important. If you end up messing up with the kernel, then you're going to lose. I mean, you're not going to get what you want to get. So that's exactly those are the problems that you would have as far as these three techniques are concerned. I have actually looked at a lot of interesting things now in this entire 4-week of our journey into linear algebra, as we would deem it fit for being applied in machine learning. And now, after going through these 4 probably weeks, and then of course you have a lot of other materials available on the web too. If you look at any textbook on machine learning, I am quite sure you will be able to appreciate the concepts which are there. As far as the idea of linear algebra applications in machine learning is concerned, you will be able to appreciate it much better. And now what we are going to do is we will be embarking on a journey into probability and random variables in the next 4 weeks. And post this 4 weeks lecture, what we will do is we will come back again with set of questions. And now I tried to answer certain questions which are posed by students on the forum and questions which were recorded and posted by our other participants of the course. In case of probability and random variables also, we will do the same thing. We will take some questions from the forum, and we will also have some interactions like this, and then we will put the questions, we will try to answer them, and we will repeat the same thing for the last week too. Namaste.